I'd like to thank the organizers for inviting me to give this talk. When I was invited to give it originally, I was told that I should talk about the protein data bank, but it occurred to me in this diverse audience that it might be much more helpful and useful for us to look at some of the key databases that exist in crystallography, because crystallography as a discipline has been unique in its development and maintenance of many databases. So this is a collaborative talk with myself, Colin Groom from CCDC, and James Kaduk, who's been involved with the creation of the Powdered Fraction File. So why do we need databases? First of all, it's safe storage for the results of scientific research. In working with the PDB, we've had more than one panicked request from a depositor whose computer had been ditched somewhere in a dumpster behind the university, and they wanted to know if we had the data, and of course we did. It's a one-stop shop for users to get information. It's a very good starting point for new research, and of course with different kinds of analysis tools, you can unlock the knowledge contained inside the database. And not unimportant is the prevention of the unintentional duplication of effort. Some people want to repeat an experiment, but many people are unaware that somebody else has done the work, and so coming to a database and seeing that it's been done is very, very useful. So there are many, many examples of data resources in crystallography, and I've listed some of the ones that we know about, and I'm pretty sure there are more. For the purposes of this talk, I'm going to spend time on the CSD, the Cambridge Structural Database, which is managed by CCDC, the Protein Data Bank, which is managed by the WWPDB, and the Powdered Diffraction File, which is managed by ICDD. So let's talk about a little bit about history, because this is a history session after all. The CCDC was founded by the Crystallography Group in Cambridge, and the initial funding was from UK research councils. At a certain point in 1989, there were various issues having to do with funding, which I'm going to come to at the end of my presentation. It was established as an independent company, a not-for-profit charitable institution, but still in partnership with the University of Cambridge. And as I've come to learn deeply, the email address is a Cambridge email address. In 2009, there were 500,000 structures available in the CSD. Last year at the ACA meeting, I met up with some of the folks, Colin Groom at the ACA meeting, and they were looking for a US place. And we had at the PDB a very nice new building, and somehow we found out the geography they were interested in is central New Jersey, which some of us like. And so Paula ran away, but it's okay. So they established a U.S. operation in our center, which is headed by Stephen Burley. The center, which is called the Center for Integrative Proteomics Research, now a little group is building up there. There are now 700,000 structures available in the CSD. So here's some nice pictures showing the various this is the original home. This is the beautiful building on Union Street where my brother had an apartment across the street, so he could always be jealous of how nice this building was. And this is the founder, Olga Kennard, and then Frank Allen, and then David Hartley was involved in the business operations. And this is the building that there's a small operation in the U.S. in Piscataway. And so these are the players and the history. So we're talking about 1965. The Protein Data Bank was established in 1971 by Walter Hamilton in Brookhaven. But there was no mandate to put any data into the PDB. And so there was a lot of work in the 80s, spearheaded by the IUCR on one hand and Fred Richards on the other, to come up with deposition guidelines for what should be in the PDB and what was mandatory and so on. And that took a long time to put together, and the guidelines were published in 1989. In 1998, the Protein Data Bank management was changed to the Research Collaboratory for Structural Bioinformatics, which was a consortium consisting of Rutgers, UCSD, and NIST. NIST at some point left the consortium. And in 2003, the WWPDB was formed by the RCSB, the PDBE in Hingston, and PDBJ in Osaka, and then BMRB, which is the NMR group in Wisconsin, joined the WWPDB in 2006. 2008, structure factors were required for deposition, which you'll see is particularly important for the data quality. And as was mentioned, 2 weeks ago we reached the 100,000 structure mark, and things continue to keep growing. So here are some interesting pictures. This is the petition that started the PDB in 1971 or 1970 as a petition, and this is the petition that Fred Richards spearheaded to say that data must be put in the PDB. This is the announcement of the PDB, a picture of Walter Hamilton with Wyckoff at Cold Spring Harbor, where the PDB first began, and a picture of Tom Ketzel, who took over from Walter, and myself shortly after this picture was taken. I'd like to point out that the WWPDB made a beautiful calendar for the International Year of Crystallography, and in the spirit of wanting to highlight macromolecular crystallography. And then this is a picture of the 40th anniversary of the PDB, and some of the many people who have been involved in the PDB over the years. For the powder diffraction file has an even longer history, beginning in 1941 in the creation of the Joint Committee for Chemical Analysis by Powder Diffraction, and Jim can fill you in on the details. There were 3 ASTM committees. In 1969, the JCPDS was formed, and in 1978, the name was changed to the International Center for Diffraction Data. And here is some pictures of the ICDD management group, which manages the PDF. Here's a picture of the headquarters in Newtown Square, Pennsylvania, which is a beautiful place. Jim has pointed out that there are regional co-chairs all over the world, which again makes, just as the CCDC and the Protein Data Bank are international organizations, so that is the case for the ICDD. And I think that's a theme that has to be if science is going to move forward. So, what is a data pipeline? All of these databases are handling different kinds of data in different kinds of ways, but they all share a set of procedures that we all have to use. The first is the data has to exist. The scientists who are creating the data have to produce the experimental information. That is then, once that happens, you then go, and that of course we all know how much work it is to get to this point. So that's where most people stop. The data resources then have to figure out how to collect the data or deposit the data. They have to process the data, get it in some form that it's usable. A big emphasis in all the data centers is data validation, with the idea that you want people who are using the data to be able to trust it. And the different data centers have different ways of handling validation. Then there's the distribution of the data in different ways. And then finally, once that happens, there have to be the ability to do data analysis and visualization, in some cases by the data centers themselves, and in other cases, things stop at this point, and the user community comes up with different kinds of analysis and visualization tools. So the data files are all done differently, but according to the standards of that data resource. So CSD is using CIF. The PDB was using the PDB format for many, many years, and now is now using MMCIF, although MMCIF was put into place 20 years ago. We began the work under Paula's leadership, and as of only this year, MMCIF is now the official standard for the PDB. And the PDF, the powder diffraction file is housed in relational databases. So the content, the CSD has coordinates, experimental data, chemical representations. There are over 700 structures, 700,000 structures. The PDB has coordinates, experimental data, 400 metadata. Metadata are the data that describe what's there, like what it describes the experiment, the ligand, the chemistry, and so on. There are over 100,000 structures, and we are at least at 10,000 structures per year at this point. The PDF has single-phase X-ray powder patterns of very large numbers of chemical types, ranging from inorganics and organics, all sorts of biological molecules. It has the interplane of spaces and intensities, physical, chemical, and crystallographic properties. There are 234 sets of 1,000 sets of atomic coordinates and over 750,000 unique data sets, as well as raw diffraction data. So it's useful, I think, to look at the growth curves of the three data centers, and they show a healthy growth, although not as dramatic as it was at the very beginning. For the PDB, I can speak for a little bit more in the sense that we do have an equation that was derived by Dick Dickerson in 1978, when there were not very many structures, that predicted this exact growth curve. I don't know how he did that. I don't get it, but it really does. Pertain. So there's a good source. There's good growth of data, which of course is linked very heavily to how much money there's going to be for science. I'll talk about that a little bit later. So the different data resources collect the data in different ways. In the early days, the CCDC took most of the data from the literature and put them into the data, put them into their archive. But now crystallographers can deposit their data directly to CCDC, and there are various agreements with publishers to put the data in. The PDB operates exclusively by the depositors putting in the data prior to publication, and you cannot publish a structure of any macromolecule these days without having the data in the PDB. And so that's an absolute requirement. And for that, we owe that really to the groups in the 1980s who set up the requirements. The PDF has contributions from individual scientists and corporate laboratories, does extraction from the literature, has a very unique grants and aid program, and has also calculates patterns from other databases, which I didn't know until I began to learn from Jim. So the data processing for the CSD, there are publications input, there are depositions by the depositors, then there's a syntax check to make sure that everything is in a reasonable form, and then there's a particular set of software that is used now to process the data. In the first pass of validation, as in the case of any database, you have to get it into some kind of a standard format. You need to compare the data to known standards, check the internal consistency of the data, and compare the data to other in the archive. And then what the PDB also faced is putting the chemical representation in properly, because when you only have coordinates, you don't really know what the chemistry is. And so you have to figure it out. And in small molecules, it might be a little bit easier than for large molecules, but that is a very big challenge to get the chemical representation correct. The scientific validation, the point for the CSD is to make the structures chemically discoverable, and that is why it's necessary to try to figure out the chemistry of what is going on, what's a double bond, a single bond, and so on. And there are expert editors who do that. The PDF assigns what's called a quality mark, and you get graded as to how good the data are. And unlike the PDB, the PDF will actually reject data if it does not come up to snuff. And that is a choice that is made by that data resource. And the details of how this is done are shown here, where you will get a major warning, for example, if your space group is wrong or your cell dimensions are wrong. And then there's all different kinds of things. All of these are the different kinds of things that are being checked before anything actually goes into the PDF. The PDB has recently created a new data processing tool that is being used by all the centers, and it was just released in January and is under heavy testing now by the community. And it involves checking the ligands, checking the sequence, checking all different kinds of annotations, and then doing validation. And I will tell you a little bit about that, about the validation. In the early days of the PDB, people did not like the idea of validation. They said, the author knows best, and don't you dare touch my structure. Then, due to some of our very active colleagues, some of whom are in the audience, and a lot of pressure, and also due to the fact that there was actually an unfortunate set of structures that are allegedly fraudulent, it became very clear that the PDB had to do much better validation. And so in order to handle that, we set up validation task forces that represent the different areas of structural biology, X-ray crystallography, NMR, EM, and now small angle scattering. And these people who were, for example, Randy Reed headed up the X-ray one, spent a long time figuring out what's the best way to check structure, and they made recommendations to the WWPDB. So now we have a lot of detailed geometry that's checked that had already been checked in the past, and this was just updated. But the most important thing was to check against the structure factors. And there's, again, very detailed checking that allows you to see if there's any serious error in the structure. And then there are various kinds of graphics that show you places in the structure that might be in error. And I think the thing we like the most is that there is a quality indicator now to give you an overall sense of the structure by looking at this graphic, and it will tell you how the structure is with respect to various quality indicators and also with respect to other structures in the archive. And then there are residue plots, and if there's red, it means there's something wrong in that residue. So that's something that has been implemented. All of this has been implemented for X-ray, and in the next 2 months or so, there will be similar kinds of reports for NMR and EM. Not as detailed because those fields don't have as many quality indicators as X-ray, but in time, we will be able to do that. In terms of distribution, the CSD does provide SIFs from the CCDC website. There is online searching by WebCSD, and then of course there's the local CSD installations in your lab or in your university. The PDB has a website, FTP site where all the data reside from all the data centers that we have. And then in addition, we have websites that give different kinds of information about the structures and tell you different views of the data. And those are maintained by the different centers. The PDF does most of its distribution via DVD and CD-ROM, and that's the way that center works. In terms of tools and services, the CSD has put a big emphasis on creating different kinds of tools and services to analyze the data. And for example, Conquest does advanced 3D searching, Mercury does visualization and numerical analysis, and IsoStar does IsoStar, which I've used, does the intermolecular interaction analysis, which is really useful. And Mogul does molecular geometry analysis, and the PDB is actually using Mogul as part of our validation of ligands. The PDB, each site has a set of services. The RCSB, the PDB-E, and the PDB-J all have search engines, different kinds of visualization analysis tools. We have a lot of educational materials that are centered around the molecule of the month that is done by David Gutzel. PDB-E has different sets of visualization and analysis tools and something called quite interesting PDB structures, QUIPs. And PDB-J, again, has many different kinds of tools, including educational materials and encyclopedia of protein structure that they maintain. The PDF this is a screenshot to show you some of the, what you can get from the PDF site. And there are also tutorials and educational material. Okay, so that's kind of in a nutshell all the different services that are provided by the different databases that currently exist. So management is quite complicated, and that's where we really differ a lot. The CCDC is a University of Cambridge Partner Institute, and it's a charity. It has an international board of trustees, and it has a total of 60 staff members to handle the data and to create the services. And there is a partner organization in Japan as well as in America. The PDB is run by an organization called the WWPDB, which consists of the three partner groups, RCSB, the PDBE, and PDBJ. I apologize, I should have BMRB, but this was a crystallographic meeting, so I didn't put that there. Rutgers is run by, RCSB is run by Rutgers and UCSD. We have 34 staff, and our funding is totally government funding from a consortium, NSF, NIH, and DOE. And this is the PDBE is run at EBI, which is an EMBL site. It has money from the Wellcome Trust and BBSRC and 25 staff. And PDBJ is at Osaka, has 21 staff, and has funding from the Japanese government. This is a complicated way of running an organization, but it actually kind of works because all of us are always under the gun for getting funding, but never at the same time. So there's always somebody who's safe as we try to get through all of this. Here's the leadership team at the current time. It's Harad Kleivik, myself, John Markley, and Haruki Nakamura. The PDBE site has had 4 different leaders since 1998. And the Japanese side has had 2 different leaders, and I have been constant since 1998. I would like to announce here that starting at the beginning of June, I will no longer be the director of the RCSB PDB, and my colleague and friend and mentor, really, Stephen Burley will take over the directorship, and I will become the associate director, so we're switching roles. And I am sure we will continue to do a good job for the community. The PDF is run by ICDD, which is a Pennsylvania not-for-profit corporation governed by a board of directors. There are 40 people who do the work of the professional staff, and there are external editors and volunteer task groups. And there are 40 grants and aid projects worldwide, which I think Jim would be happy to talk to you about. So there's always been this discussion in the community about funding, and the PDB is free, we're told, and the other people charge money, we're told. But everybody, the money has to come from somewhere. And so somebody has to pay. There are grants, and if the PDB gets grants, then that's so much money that is gone to the PDB. Subscriptions, financial contributions, there could be deposition and curation fees, there could be licenses, industrial partnerships, philanthropic contributions, or some mix of all of these things. And I've been involved in several committees that have to do with what is the right funding model for domain repositories, because there really isn't one right answer. And in our community, we've chosen different ways, and I've just summarized what we've done. The CCDC is a charitable not-for-profit organization. They get contributions from academic users, which helps maintain the CSD, and the commercial users help develop the applications, provide the money to develop the applications. The WWPDB, as you've heard, is funded by mostly grants and some foundation money. We also have a foundation of our own, which we can use to help fund various educational initiatives. And the ICDD is a not-for-profit organization, and most of the revenue comes from licensing the PDF databases. So these are different ways of making sure that these data resources stay alive. And if you go out in the broader world, beyond crystallography, there are many different groups who are struggling with what's the right way to pay. It costs money to archive data, and someone has to pay for that. So what are our challenges? The three challenges that I see are the rapid growth of data. There doesn't seem to be any danger that we're not going to have more data, and we have to somehow be able to manage the data. And we have to ensure the data quality. All three organizations that I've spoken about spend time on data quality, and it's a balance between the data that you have to maintain and how good should the data be. And some of the issues that come up have to do with should you reject structures. The PDB does not reject structures. Apparently PDF does reject structures. Whether that's the right thing or the wrong thing on either side is debatable and something that the community has to think about. And the single greatest challenge, I think, for all of us is the sustainability of data resources and how to find the right kind of funding model that will keep these data resources going. And I think you've seen in all the cases that there were different models over time for how to manage the data. And I think that, and how to pay for that. And so I think that is the thing that we should be most concerned about. And then finally, I just wanted to acknowledge the people, and this is only some of the many people who've been involved in the PDB. This is from 2 years ago when we had a celebration of the 40 years of PDB. This is a picture of the CCDC staff, and this is a picture of the ICDD staff. This is Jim Kaduk, and this is Colin Groom. And I thank you for your attention.